Okay, good afternoon, everyone. How are you? Good. So we have two very exciting talks. We have two hardware talks in a row in this room, so you probably want to stick around. And starting this block, we have Preston Holmes with his talk, Blending Art, Technology, and Light, Python for Interactive and Real-Time LED Installations. So let's give a hand to Preston.
All right, hello, thanks for coming out. My name's Preston. I do a few Python things, I do some cloudy things, and I have sort of a closeted artistic side that I'm guessing some of you have some interest in art and creativity. I'd actually argue that almost everyone here at PyCon is a creative person because code ultimately is a creative process. But why am I going to talk about LEDs? And the answer is super simple. It's because for forever we've been fascinated by twinkly lights, whether it's looking at the night sky, staring at fireflies in a forest, or sort of oohing and awing at fireworks in the sky. And working with LEDs has a lot of parts, and so what I'm going to really try to do is give a full stack overview of all the layers here and go all the way from electrons to emotions, talk about the LED as a material, the controller hardware and some of the integrated circuitry involved, interfaces and protocols that are required to speak to these devices, some of the software and libraries that can be used, and then finally some creative design patterns. So it's quite a full stack, so we're going to just dive right in. So LED, light emitting diode, I'm guessing everyone can understand what the light emitting part is by default here, so I'll talk just very briefly about what diode is. Diode essentially is a two-layer sandwich, two semiconductor materials where one half is doped in a way that has an excess of electrons, and the other side is doped in a way that has sort of a shortage of electrons. These are called electron holes. And this results in a structure where current can really only flow in one direction. So they're used in circuits to act as sort of check valves. And in the case of light-emitting diodes, what happens is when that electron drops into a hole, it goes from a higher energy state to a lower energy state and releases a photon, which we can see as visible light. And so many of you familiar with this form of LED. This is kind of the blinky light that you always start off with as a hardware project, but I just want to show that the LED material is sort of that one small square. And for more creative purposes, we're interested in RGB LEDs. And these are, in fact, three separate LEDs closely put together into a package like this, where each of these have been chemically set up to emit either red, green, or blue light. And in this case, it's in what's called a 50-50 package, which just means it's a 5 millimeter by 5 millimeter square. And by having them this close together, when you apply different amounts of power to each of the red, green, and blue LEDs, the colors blend, and we can perceive it as a full spectrum. And when you start working with LEDs, one of the terms you come across really quickly is smart versus dumb LEDs. And a dumb LED is simply one of these LED packages that has no logic circuitry involved. It's just you apply voltages and they emit light. And if you have a strip of dumb LEDs, when you apply voltage and you make purple, all the LEDs are the same color at the same time. Smart LEDs involve some sort of logic circuitry, and this is some sort of integrated chip along the way that allows it to receive a data protocol, and each light along the strip can be individually controlled as its own color, own brightness, etc. And they've actually now gotten to the point where they're building these integrated circuits directly into the LED package. So these things require these sort of protocols, and there's a variety of them. But before I get into that, these packages come in different shapes and sizes. So there's some varieties here where there are more than one LED per control chip. So this unit of control is called a pixel, often called an LED pixel. And an LED pixel may have more than one LED in the package. So they come in a variety of forms, but the unit of control is called a pixel. And the data types they take tend to be these sort of specialized, very high clock rate serial formats that essentially boil down to an array of bytes. And each of these chips will simply pop off 3 bytes, use it for RG and B, buffer the remaining bytes, and then forward them down the line, so that each pixel along the chip doesn't really know that it's pixel number 5. It just simply pops off 3 bytes and forwards the remaining. And these protocols, while they vary, they're all very high clock rate and very precision timing-oriented protocols, and they're not something that a sort of kernel-based, operating system-based program can generate reliably. You need something that's going to maintain really high fidelity in the timing. And so what kind of things can you use to create these signals? Well, you can use an Arduino, and there's really actually a fantastic Arduino library called FastLED. But the limitations of Arduinos are that there's a limit to how many of these pixels you can actually connect to one at one time. And since we're here at PyCon, I just have to be a little sad. You can't really effectively use Python directly on Arduino. So what sort of some other choices there? And in the do-it-yourself hobbyist space, these are kind of the two main players. There's varieties of them, but these manufacturers. And what these boards do is they take as an input a standard lighting protocol, which I'll talk about in a second, and they have embedded in their own circuitry, in their firmware, the ability to translate into a whole range of the different pixel-specific timings and formats. And they have enough capacity to allow you to plug in many of these pixels. So this is the kind of board that you'll often use, and I have one up here that I'll demo God's being willing. So I said these take a lighting protocol input, and so to talk a little bit about that, I'll have to tell you about DMX. Actually, not that DMX. This is DMX 512, and it's the lighting protocol that was initially established for theater lighting. So real quick bit of history is initially all the stage lights in theaters used to have manual dimmers that were right up at the front of the stage, and that got to be kind of painful. So they initially created DC motors that would turn the dimmers and control the DC motors from the back of the house, and that was sort of cumbersome. So eventually it became serialized into this protocol called DMX 512, and it's able to address 512 individual channels of data in this sort of slots, 8-bit slots. And initially, I'm sure this is called one universe. 512 channels is called one universe of DMX, because I'm sure it was sort of the cliche of 512 channels has to be enough for anyone, right? No one's going to need more than 512 channels. Well, things grew, things got more complex, and they did. And so eventually, you have to run multiple paths of this serial cable to control more than 512 channels. So the evolution of the protocol moved towards wrapping these data packets into Ethernet packets. It has a very catchy name of E1.31 as the standard in the lighting industry now for sending DMX over Ethernet. And it is, in fact, this protocol that has now become the most common way of controlling the lighting circuitry. Well, that's sort of really, now that we're talking about Ethernet, we can start talking about software that runs in a familiar sort of operating system environment. And let's talk about that. There's a lot of this software out there that's very specific and is monolithic, and it simply handles the rendering of data and then the translation of that data into a protocol. If you're interested in quickly hacking on something that's not so interesting, you'll probably be more interested in looking at something that allows you to use a library that takes data and does the conversion for you. So for us as sort of Python programmers, we want to be able to leverage something like an interface library that handles all the specific protocol format. We just want to give it an array of values. Just to give credit, there's a project called Open Lighting Architecture. It's sort of the Swiss Army knife of lighting protocols, tools. You can give it data, it has great Python bindings, and it will render it out to any of the various hardware types out there. And it's very flexible, but it's kind of a kitchen sink. It's a bit heavyweight, and for a while until recently, it was hard to get to run on something like a Raspberry Pi. So I went ahead and wrote a pure Python implementation, a minimalist implementation of just that E131 protocol in Python, but they're both perfectly usable. Now, that layer of the software takes care of talking to the hardware, but it's not where the creative process happens. And so when we look at the side of software that is user-focused, user sort of purpose, there's a set of software I'm not really going to talk about in the theater industry that's mostly around scenes, switching scenes. A lot of the innovation in dynamic displays has come from the Christmas lighting folks. They are the ones that do the crazy animated Christmas light shows. And for a long time, before there were RGB pixels to work with, you still had a relatively small number of channels to work with, and you'd end up with a program that often would just take the approach of dividing time into slices. So that one row is one of your channels, and then you slice that into columns, and you simply address a level or a value in each square of the grid. But when you start to get many, many, many channels, kind of individually filling in all these boxes is pretty tedious. Another approach to the current sort of state-of-the-art is DJ matrices, these big two-dimensional matrices that are in nightclubs and those kind of things. And there's very expensive, this is several $1,000s to use. Just takes sort of screensaver imagery and projects it onto a 2D matrix. So starting around in 2010, I started thinking about a way of experimenting with another model of taking an abstraction of three layers of inputs, elements, and outputs, where the inputs would be sort of events that happen from some sort of device, input device or other sort of file. These would trigger actions and elements that would take care of rendering the data over time and then ship it out to output. And this library is called Birdfish. It's really just my sort of test bed, sketch pad for experimenting with some of this stuff. It's got lots of rough edges. It's really your classic terminally pre-alpha side project. So this is I mean, it's what I'll use for the demos here, but it's not, I wouldn't go run Disney's Show of Lights on it. I talked about the input, so we'll start there. An event really, in this sense, falls into two categories. Either it's a trigger event, and a trigger event is, you can think of it as simply a light switch, on, off, and these on-off events occur over time. And each channel in your lighting system can have its own series of events, so you get this sort of player piano look to it. And this player piano analogy is not without some well, you'll see impact later in the sense that music, I've learned a lot from what electronic music has done around rendering effects in real time with sound. A lot of it applies to music. So trigger events are one type of thing. These are very discrete on-off events. And then the other type of event are what are called map events. And the analog to this is if you think of turning a dial. These are values that change in a very varied way over time. So the overall model looks a little something like this. You have events that are coming in as a timeline, either trigger or map. These events land onto these elements, and the elements are code objects that respond to triggers on, trigger off. And it's these objects that take care of generating data over time and end up resulting in sort of a torrent of data, because the hardware itself only cares about an instantaneous value, but to get any sort of an effect over time, you need continuously changing streams of data to get the hardware to do anything interesting. In terms of the actual hardware to create the events, I've kind of used primarily two. One is MIDI, which is what electronic musical instruments use. It's older. It's pretty reliable, but it's limited to 7-bit values, sort of 0 to 127, 16 channels per sort of MIDI bus. And they often involves a lot of OS-specific driver level stuff that can be kind of a pain to work with. Open Sound Control is a bit more modern. It's UDP based. I won't use it for the demo today because wireless on a live demo is pretty painful, but and it's very flexible about how you specify the values. So this graphic is actually of a program called TouchOSC for iOS. They have an Android version as well. And what it does is it allows you to sort of give a URI essentially to some value you want and give you either floating point values for any range of these controls, or you can set a minimum and maximum. So very flexible, gives you that sort of raw controller input that you can then turn into something of your own choosing. All right, let's get into a little bit of actual Python now and some code. So essentially, this is the minimal starting point for some sort of Birdfish-based light show. The light show itself is the object that takes care of rendering the main event loop. It's the primary orchestration object in this. You then bring in a dispatcher for the events, something that's listening to input hardware and sending triggers to the specific light elements themselves. And then finally, you need some output where the data gets sent to be turned into hardware actual events for the lights themselves. The next step is to actually create a light element. This is the thing that takes triggers as inputs and renders out data every frame as far as what it should do. So it receives a trigger on, it says start sending channel data out to the lights, trigger off, stop sending channel data out to the lights. You then have to kind of wire up some of these pieces. You have to add the output network to the show so it knows about it. You add the element to the show so it knows about it. And then finally here at the bottom, you tell the MIDI instrument, in this case I'm using a nanopad controller, that this button, which gives MIDI note 49, I didn't decide that, that's just the way the hardware is built, this is the thing that should be connected to that lighting element. So if the demo gods will, and then finally we go ahead and we start the dispatcher, the MIDI listener runs in its own thread, the show is a blocking, run loop, and we'll see now if I can get this to. I've had some issues with my USB-based, and the demo gods are not working with me today. So my backup is video. So I can show you what this would look like were it working like it was earlier. So you touch the button, and you get the light comes on. Release the button, light goes off. That in of itself is not very creative. So the next step really is to look at what can be done around giving things a more organic feel. Things in nature don't start and stop very suddenly like that. And so the people who first started working with electronic music realized too that musical instruments have sort of inertia and sound, and things come on softly and then go off softly. So there's a concept in synthesizers called an attack, decay, sustain, release envelope. And if you think about what the volume of an instrument is as you hit a key on a keyboard, things can come on gradually, reach a peak, decay, sustain for some time, and then when you let go of the key on a piano, like when you have the pedal down, the sound falls off. So we can use that same concept in lighting amplitudes. Oh, I'm actually going to have these out of order. So this is to show that an element doesn't have to be a single light. An element can be a group of lights. And that the trigger in this case is still a single trigger, but it now affects a whole group of lights. This is the demo to show what happens if you have an envelope. So in this case, there's still a single simple trigger on, trigger off, but the lighting element is handling the rendering of the fading on, fading off over time without it being required from the control side. And so it's still rendering 40 frames per second worth of control data. And the same idea can be applied to an array of lights where the behavior of this element is called a light chase, so that the behavior over time of which light in an array is lit is being determined by the light element. The trigger itself is still just a simple on-off, but in this case we're getting to add sort of a slightly more complex layer to it. The other thing when you get to this idea of envelopes is that animation has always brought in this concept of tweening elements. So a tweened element is something that tends to ease in and ease out, and the idea is to have non-linear motion gives a electronic device a more natural and interesting, it gives you more creative flexibility. So if you had simple animations in a 3D animated movie that moved only linearly and stopped, they wouldn't look very interesting. So you can apply a range of these creative curves, not only to brightness or motion, but you can apply them to things like the rate of change of color, the rate of change in saturation, the rate of change of two things at once. And so you can create these envelopes of change over time and build them as attributes of the behavior of one of these lighting elements. And I have more great demos I'd love to show you, but I believe that once my hardware has fallen down, it's fallen down. Yeah. I miss my MacBook that had a hardwired Ethernet port. All right, so not to dwell on that, here's just some examples of some of this sort of nonlinearity that you can get. So you can see a sort of a spray pattern where essentially the velocity is changing over time, slowing down. That's one effect. This sort of shows some elasticity in the motion where there's a little spring back. And it also shows there's another envelope applied to the edges of that light curve. The way it fades off from the bright point in the center to the edges gives it a sort of soft edges. There's even a further trick in this demo where I have sort of sub-pixel anti-aliasing so that the center point of that motion is not lockstepped to a single point. And just one more. Yeah, this is sort of a bounce motion. So the key is to remember that we started with the simple LED material, and we're working with hardware that is completely dumb about what it renders out in terms of the lighting hardware. It just requires an instantaneous value to give a certain brightness. Anything that looks like behavior has to come from the software itself. And that's sort of what I was looking at in terms of trying to build a toolkit for building those kinds of effects, and in a way that could be sort of worked with in a real time that isn't being pre-rendered. Let's see. So I actually have, because my demos have failed, I have one more bonus material I will go into, and that is around the idea of adaptive frame rate. So I talked about, to get something to look like motion, you need sort of at least 10 to 12 frames per second, and that looks kind of jittery. If you've ever worked with flipbooks, it's sort of, flipbooks are maybe in the 10 frames per second rate. To get something more fluid, I mean, if you're a video game person, you want those super high frame rates. So I shoot for around 40 frames per second. The problem is that depending on how complex the effects are and how many of them you're trying to render in real time, that can be taxing on the CPU. So the goal is, how can you come up with a way of consistently delivering the expected effect to end or be synchronized at a certain point in time if your frames start taking longer to render? So in this case, this is the ideal scenario. Every frame of these 20 frames across 1 second are being evenly calculated, and we end a color fade. Each of these dots is sort of like represents a light in an array. The yellow lights represent one of these chases across front to back, and then the color fade. The problem is that if one of these frames takes a while, we still want to end at the exact same place at 1 second in time. And so the idea is to come up with sort of this adaptive loop where at the beginning of each loop, I anticipate what's the next expected frame, end time frame, calculate all the values, and if I am done ahead of time, I can just sit around, wait, and ship the data off and then begin the next loop. However, if I'm overdue and I've missed the mark, I can reduce the frame rate so that the next frame I calculate, I'm giving myself more time to calculate, and sort of give a feedback to what the frame rate is at any given time. And this kind of I honestly don't know how other games or other systems do it. This is something I was kind of just came up with to address my challenge here. And the result is something that looks like this, where we now have taken 16 frames to do it instead of 20, and a couple of those frames have taken longer to render, but the end result is that at the end of 1 second, we still are where we expect to be in the overall effect. That is what I have. So go forth and be creative. And we certainly have some time for questions, and if you want to chase me down, I can try and reboot this demo and see if we can get it going, but I'm not too worried about that. So thank you.
So thank you, Preston. And if you have some questions, please form a line here in the mic and state your question.
Hey, first off, great talk. It's good to see how far you've brought this, as a medium. Obviously, it has the hardware component, but the idea of like DJing with light is really cool. Where do you get started as far as like equipment? How do I, go and get the things I need to play with this stuff?
Yeah, I mean the availability of the smart pixels is become better. It used to be I'd got a lot of my actual lights from China direct, sort of through Alibaba Express or one of those types of places. But the hobbyist boards are available. They're pretty cheap. You can actually buy them as kits or buy them assembled. And then a number of sort of the SparkFun and Ada type plate stores have some of the pixels now. But you really can't play with the software until you have at least some of the hardware, because the software by itself is pretty boring.
Hi. Oh, that's pretty bad. I'm just wondering, there are frameworks that seem well suited for this kind of thing, namely processing, which connects to a lot of different hardwares and software elements. And so I'm just wondering if you think there's any particular advantages of choosing Python for an application like this, and where its strengths might lie.
Yeah, I mean, I would say that against processing, there is no particular advantage except that I'm a Pythonista and it's my tool of choice, and I'm not gonna really try to claim it's better. I think one of the strengths Python has in many of the domains that it might be used is that there are lots and lots of resources out there for connecting other things into it. So there are lots of ways to integrate, a web server loop, or there's just lots of the breadth of sort of the Python ecosystem allows you to tie this part of it, a lighting system, into anything else that Python might be connected to, and just leverage the breadth of the ecosystem. But as far as the actual rendering of effects, processing is phenomenal. And I know people have done amazing things on Arduinos with processing. So. All right, thank you.